Thanks everyone for logging in. Thanks everyone on YouTube. Hello out there in the world. I think we are streaming to you. I'm going to start the recording for the in-class students in just a moment. So just if you want to keep your camera on, that's fine, or off is fine. Record. All right, thanks everyone. Welcome back to the Water, Wetlands, and Watersheds seminar. This week we have a really exciting presentation. And I'm going to leave it to my colleague Andrew to introduce our speaker today so I don't mangle her name. But thank you very much for speaking with us today. Andrew, if you could please introduce our speaker.
Great, thanks David for that introduction. So today I have the pleasure of introducing Bregje van Wesenbeeck. She is based in the Netherlands, and she is currently a senior researcher with Deltares Institute of Applied Research and Delft, and she's an associate professor at Delft University of Technology in their civil engineering department. But Bregje and I have a kind of a common history, which I'll just share briefly because I think it says a lot about what she's doing right now, and that is that we're both trained as ecologists through our graduate work and a lot of our research, but she has kind of sped away or kind of, I think, act as an ambassador of that kind of discipline in the field of engineering, and really is sort of at the forefront of this effort to blend ecology with engineering for coastal sustainable efforts. And so I've really valued sort of watching Bregje's career develop, as well as many of her sort of colleagues in the Netherlands, because I think that the Netherlands, because of their constant challenges of the onslaught of the ocean, sort of offer a crystal ball as to the challenges that the rest of the world is just now starting to become engaged with. They have hundreds of years of experience. And so if you want to like sort of a look into the future in terms of challenges that we'll be facing and what solutions might be available, I think you look at the Netherlands and the work that's being done there. And so it's really kind of think a valuable perspective to hear from someone like Bregje and hear about what she's involved with at this time. She's worked internationally in the Netherlands, Indonesia, Philippines, here in the US. She does a lot of work for the World Bank and Asian Development Bank, for example, as well as some NGOs that we're familiar with like TNC, CI, and WWF. Who come to her for expertise in terms of kind of restoration and mitigation type work and just general challenges related to coastal engineering. And she's publishing well. So in addition to doing this very applied research, she's publishing in basic scientific literature, such as the Nature family of journals, and both really straddling the worlds of ecological engineering and ecology, which is evident in her publications. So, and she's teaching courses, including Building with Nature. All right, so I don't want to take any more of Bregje's time. That's an introduction to sort of, I think, where she's coming from and why I think we're lucky to have her speaking with us today. So.
Thanks, Andrew. Bregje, you can go ahead and share your screen, and we'll thank you for calling in at what is approaching 6 o'clock in your time. So I know it's probably getting like dinner time, and feel free to have a glass of wine if you like, whatever you want. The floor is yours, so go ahead and share your screen.
Thank you. Thank you, David. Thank you, Andrew, for introducing me and for inviting me. Actually, it's a pleasure to be here and to be able to talk to you. Can you see my screen? I think you can.
Everything looks good, yeah.
Okay, cool. I'm going to put it in presentation mode. Yes. Okay. Let's see if I'm going to be playing a little. I want to move it to here. Yeah, this works better for me.
We don't see it in presentation mode. It's the regular slide.
Yeah, that's strange. I'm still. Yeah. There it pops up. Yeah.
Perfect. Looks great.
Yeah, that works better for me as well. Okay. I will talk a little bit today about part of my work, not so much about the implementation work I'm doing, but a little bit more about the research behind it that we've been doing on nature-based solutions for flood risk reduction. This nature-based solutions topic has an immense global attention right now. We just had the last 2 days, we had the Climate Adaptation Summit in the Netherlands, and there was a huge interest for what can nature do in helping us to adapt to climate change. It's called nature-based solutions. IUCN made a definition for that, but basically it's making use of ecosystem services, right, for functional purposes. I mostly look at how ecosystems can help us in coastal adaptation or in rivers for flood risk reduction, and how we can better and more naturally manage our rivers and coasts. Well, other terms that in the Netherlands we call it building with nature. Sometimes I think in urban context or your environmental EPA, what is it? EPA calls it green infrastructure. That's when they started. You have the living shorelines, of course, in the US. I stick to the term nature-based solutions. Okay, I think most of you probably know this, right? But basically in the world, there's increasing risk, and risk is a component of the hazard. So the natural phenomena, its intensity and its probability of occurrence, and of exposure. That is what constitutes risk. And exposure is basically the people and assets that are exposed to a hazard. So that we face increasing risk has several reasons. It's because the hazard component is rising due to climate change, for example, increased rainfall, but the exposure component is rising as well. So we get more people that start living in vulnerable areas or in delta areas that are low and sinking. For example, we're damming rivers that then don't bring sediment to deltas anymore, while we have increasing delta cities. So that is what makes actually that there's increasing risk. I think it's sometimes good to distinguish also between, well, there's of course risk on flooding, fluvial flooding, so by rivers, coastal flooding by the sea, but also pluvial flooding, so stormwater running in cities because there's a lot of area that's impermeable. So different types of risk. Here I focus still on flood risk and mostly on waves and wave attenuation. What is our response to risk? Well, of course, in the Netherlands, this used to be our first response to reducing risk, right? We would build seawalls, levees, dikes, and it's still what people think about in their heads when they think about how do we reduce risk, how do we keep ourselves safe protect us against the water. That's really that used to be the Dutch sort of mantra. So we built these big seawalls, and this is more the nature-based solutions. And then there's a bit of the question about it. Well, this is mangroves nature shield against typhoons and tsunamis I put in. So there's what can nature actually protect you against? That's the question for me. And I think as scientists, we should sort of distinguish fact from fiction, right? And I think mangroves and tsunamis, for example, the debate is still out there what they do and how much mangrove do you need. So after the Asian tsunami, there were some science articles about it. But if your mangrove is not wide enough, villagers also get trees on their houses. But if the mangrove is wider, there is anecdotal evidence that they do protect villages against tsunamis. So how do we actually start working with these ecosystems? Well, it's not always based on ecosystem restoration. It's often, this is what happened after the Asian tsunami in Aceh in Indonesia. They start planting these mangroves in this area that was completely wiped out. All villages were wiped out, and this was the response. But you can already see, as I think a lot of you will be engineers, I mean, if we look at engineering and at performance metrics, at how much risk can we reduce with a solution, what return period does this levee protect us against, this mangrove will not do a lot if there are these small sticks. And basically to say that these mangroves will protect people against tsunamis is giving people false hope. So this is what we sort of started to work on. Let's try to make these solutions make people safer and not less safe, basically. So how do ecosystems behave under extreme forces? This is what you don't see in the newspapers, but this is what a mangrove looks like after a wave of 7 meters high has passed through it, right? I mean, these forests get pretty beaten up. There's good pictures that I could have put in, but if you look at the Louisiana wetlands, what they looked at after Katrina, I mean, like acres of wetland were completely disappeared. So I mean, to work with nature and to have nature as part of your, let's say, coast or riverine protection strategy, we should really know what happens under these extreme forces with natural ecosystems. And of course, this system and the Louisiana wetland during Katrina dissipated a lot of energy. So it did something that was beneficial. But like I said, only if it's strong enough so that those trees get not thrown on your house, and if there's trees behind it, right? And we can calculate with this. And I think that is a challenge for the future that we're trying to solve. So what started it when I started working in this field, it was basically that engineers said, well, these ecosystems, they don't do anything under extreme conditions. So for example, in the Netherlands, we design levees with a 1 in 4,000 year return period, or a 1 in 10,000 year return period sometimes. And we don't have field measurement evidence from those high return periods, right? Because they hardly ever occur. So we start looking in the field evidence, and the field evidence out there was really mostly under benign conditions. So if we say how much waves can be dampened by a salt marsh, we look in the literature, and there were a lot of measurements, but they were with like 1 meter water, 20 centimeter waves. And then we would use numerical models to scale that up to more extreme conditions. So say, okay, then we use this dampening coefficient and we transform it to a 4 meter water and 1.5 meter high waves. Now that doesn't work very well, because vegetation responds differently under a high wave versus a low wave. So what we try to do is use experimental evidence. So from flumes, from small scale flumes, there's a lot of experiment in small scale flumes that look at how does vegetation behave under waves, how does it sway, for example. But those results are also, again, difficult to scale up. We don't know when it's uprooted, for example. It doesn't, you have to scale your vegetation. There's a lot of edge effects in these small flumes we're finding. So what we wanted to do is actually do it in bigger flumes, so real conditions, to test what is the performance of vegetation under more extreme conditions with real vegetation that's not scaled, so that we can also look, for example, how does the marsh bottom behave? Will there be erosion? And that we can have a control, which is also very difficult in the field, because there has been now a lot of more measurements focusing on these extremes, but still we never have a control. So we have a storm running over a marsh in the Netherlands. We have some measurement with 1 meter high waves, but we don't have the measurement without the vegetation or without the marsh in place. And that is what you can do in these big flumes. So we start setting up a program for testing in controlled situations with controlled conditions in the big flumes. We have to do it experiment by experiment, because working in these flumes is extremely expensive. And the most expensive is the cost for building something like a marsh or a forest in the flume. Then we have 2 weeks of measuring, and then we have to sort of do the demolition of the whole setup. So I will first tell a little bit about the marsh work, then a little bit about floodplain forest work that we did in these flumes. So this is one of the very first things in 2013. We did this for the Dutch Delta program, and one of our engineers modeled a marsh, and it's a funny marsh. It's a small marsh in front of a levee. It was done for the north part of the Netherlands, where we have several kilometers of marsh in front of our levees. And there's always a question, do these levees need upgrading? Do they need stone layers on top of it? Or is the grass layer enough? And then we sort of calculate with the marsh, but only as we have the input conditions for the hydraulic models, and they are taken on the marsh. So they take into account the elevation of the marsh slightly, but they don't take into account the last 100 or 200 or 300 sometimes meter that the wave travels over the marsh, and they don't take into account the vegetation. So in the beginning, the engineer said this marsh doesn't do anything. We don't need to account for it at all. And then we did this a couple of model runs with more extreme conditions. So this is a 1 in 4,000 year hydrological scenario with high water levels, high waves. And if you look at the lowest graph, Yeah, I want to point at it, but I can't, of course, it doesn't make sense. And you look at the top right of the lowest graph, that is basically a marsh of 200 meter long that extends 2 point something meter, 2.3 meter in the in elevation. And it still reduces with a 1 in 4,000 year storm, it still reduces about 30% of the wave height. And that means that we're not in the margins of uncertainty of our levee design anymore, but that this marsh reduces so much of the wave height that we can actually have a lower or a less a lower or a levee with still a grass layer on top of it. So that means that it can be an enormous cost reduction. And then, of course, we're the Netherlands, so then everybody's interested. So this is how we started out. Also, the same model was run where the marsh was like this body of sand, and they looked at, will this sand be moved completely out or not? But it stayed in place, and it took an equilibrium profile. So they said, okay, maybe then this marsh will likely also stay in place because it's more consolidated. So then we started really looking more into it. These are some measurements from the field and a model study of a PhD student who already finished. And this basically shows when is vegetation, does it contribute to the wave reduction? And on the y-axis is a contribution of vegetation, and on the x-axis is the water incoming wave height and water level ratio. And basically, if you move to the right on the x-axis, conditions are more severe, higher water levels, higher waves. And you see that with higher water levels and higher, the contribution of vegetation is most in the middle. So with very low water level and low waves, it doesn't do that much because those waves are difficult to dampen. But then it starts to increase this contribution of vegetation. But when with really high waves and high water levels, it also does less then, because marsh vegetation is flexible, of course.
Bregje, you should be able to move your mouse and it may appear on the screen, then you can use it as a guide. If not, I'll try to annotate as you speak.
Do you see it now?
No, do not.
I see it. Yeah, I can't. But I will try to explain then in
No
words.
problem. I'll try to draw with you while you're talking, okay?
Cool. So we started doing these flume experiments. This was, I think, in 2013, 14. And we did this in Hanover with University of Cambridge, together with some German universities as well. And we got a marsh out of the field. There was a German project where they strengthened a levee and they had to widen it, so they were impacting the marsh anyway. And they gave us these marsh blocks, and we transported them to the flume. And then we placed them in the flume. There was a sand body and a concrete platform and a sand body in the middle. And then they were glued together with clay, and they were just shuffled in there. The sides were removed. So we actually glued the marsh together. It was a 40-meter long marsh, consisting, it was a bit strange marsh. There was atriplex on it that became really tall when it was still in the box. So you see that drifting up when we submerged the marsh actually with water. And then we were able to test with some higher waves. Also, we did waves till a meter. It was the first time we ever did this. We were extremely afraid. We were okay, because you have to imagine these experiments cost several $100,000s, up to $1 million to do it. Not calculating all the time, all the calculations, all the data processing afterwards. So this experiment only was, I think, about 400,000 euros. So we were extremely afraid that you do the first run and that you remove a block, and then your full experiment is for nothing, but you've spent all the time in construction, all the time. So, but basically nothing moved. So we had some results, but I think that is why we didn't put the full pressure on it, which is, in retrospect, it's a bit of a waste. So we did, here you see, we did waves up to a meter and not higher. I mean, we should just have killed the marsh in the last run or something, but we wanted to have a control. So you see our highest wave height is on the x-axis. So that's the incoming wave height. And you see the wave height reduction on the y-axis. And what you basically see is the filled diamonds are the runs with vegetation. And you see that the reduction increases with wave height, like we saw in the model and field measurement results as well. And you see it then flattens off when you increase your wave height, because wave height is just not linearly, so reduction is not linearly coupled with the wave height, basically. And with your wave height, of course, also your period increases. So what we typically see in these experiments, once your wave period starts to be longer than the length of your vegetation test section in the flume, your effect is going to be really small. So that's why you want to have a long test section, because you can have higher waves with a longer period. And we basically also see this kind of shift in where it doesn't flatten off. And I think there's two things that could have happened there that we measured. Around 60 centimeter waves, this atriplex that had a woody stem and was floating was removed out of the experiment. So we lost a lot of biomass, which could have caused the dropping reduction. But what also happened is above 60 centimeter waves, the vegetation started swaying with the waves 180 degrees back and forth. So the drag on the vegetation likely suddenly then becomes lower. So it starts to sway, so there's less friction basically of that vegetation because it's completely flat. So that is what we measured. The open diamonds are without vegetation, and you see that the reduction effect of the marsh without vegetation is still rather high. It's still around 10%. And I think if we look at the model, so we did a model validation over this, that's not in here, but our models definitely underestimate the effect of these stubbles, for example, that they have on the reduction of the waves. And we use this, of course, to actually recalibrate some of the vegetation models. So if we move on, we use these models to look a little bit at management regimes of marshes. Oh yeah, what's interesting to tell about the Flume experiment still is we also measured the bottom of the marsh, and we didn't see any movement so there was no erosion. So the bottom was well protected by the plants. And it stayed completely intact. So here we did some work on management regimes. We did this together with people in Louisiana. And we looked a little bit at, okay, so what does this vegetation contribute? Now we had better models, and we used these models to compare between the Netherlands and Louisiana marsh. And you see above in the Netherlands, we have, of course, more natural marsh. You see in the above picture in the back, you see the more natural marsh with just higher vegetation. But we also have marsh areas that are severely managed and grazed. And we wanted to know, is there a difference in how much they reduce the waves, because those areas are in front of levees. And then below is the Louisiana marsh. That's a bit different. So the above one in the Netherlands is man-made, created marsh or man-restored marsh by putting brushwood dams there. And above is a more natural but also fragmented marsh of Louisiana. And we compared, and you see the filled circles are the marsh in Louisiana. And you see there the wave reduction increases with the percentage land on the transect a lot. And you see for the Dutch marsh, they are really long, those marshes. So the percent land on the transect is larger, but the wave reduction is considerably lower because of the grazing. So this is another illustration showing that the management regime of your marsh actually does matter, and the vegetation does matter, and the way you manage and maintain it does matter for your wave reduction. Yeah, there's some historic evidence of marshes that we recently looked at. So building this whole body of marsh work and what they do under extremes. There was a historian of the University of Antwerp, and he sort of came upon some old maps from the Netherlands. And basically, if you look at very historic evidence, in the past, we used to build levees that were less strong behind marshes. So this old knowledge has been there, and we've forgotten it, and the Dutch engineers have forgotten it somehow. So we wouldn't strengthen our levee all the time when it was behind a marsh. And then he found old maps where you had all the breaches during two floods, and it was the Elizabeth flood, we call it. It was 1810, I think, and many people died. And we had the other big flood in 1953, and we also looked at breaches in these floods. And you see, these are not the graphs that were in the publication this year, but I took these because I found these more clear. The number of you see the number of breaches per kilometer dike, and then the marsh width in front of the dike. So you see the longer the marsh is, there's a large reduction in number of breaches in these historic floods. And then you see the marsh width in front of the dike, and you see the total breach width. And the total breach width actually is reduced a lot when the marsh is wider. So it means that first, a levee or a dike, a levee is less likely to breach when there's a marsh in front of it, even when it still was under-designed or less strong in historic times. And then also we find that once a levee breaches during a flood event, the breach, usually what happens is, of course, is water squeezed through, and then this breach starts to deepen and to widen. But when there's a marsh in front, that marsh stays completely stable. So we added this up with the modeling exercises. That marsh stays stable, and that breach will stay at the same size. And that can actually reduce your impact after failure enormously. So moving to woody vegetation, well, we had these experiments for marsh vegetation, and of course the main thing of marsh vegetation, what is also makes it difficult to put it in numerical models, is that it's flexible, and that this flexibility and the movement of flexible vegetation changes with your wave height and your wave period. So how much it sways from one side to the other. And that influences how much waves it attenuate, how much the percentage of wave attenuation is in the end. So this is a case where we implemented actually some natural design in the Netherlands very recently. It was part of the Room for the River program, and in the back you see the old river. You see where in the back you see the river, and in the front with the green lines around it is a fortress. And that fortress, the dike used to be actually alongside of the river. But then for the Room for the River program, they needed to depolder to actually lower water levels in this river. So they depoldered this area, and they had to build the inner dike around this fortress area, but that was a high-end real estate. So there were kind of rich people living there. They said, we don't want a levee in front of our fortress. It will spoil our view. That fortress is a historic part of the Dutch waterlinie, we call it. So it's a protected historic landscape. So we made this design where the levee could stay a lot lower. It has a very long gradual sloping back. And in the front, it has willow trees. And those willow trees actually get the waves out of the water so that we can have the levee more than 1 meter lower. And it is when this polder submerges, basically, with high water levels, and when the wind would come from the northwest, we could get waves that are 1.2 meters near the toe of the levee. So we did a small modeling exercise. How much reduction can we do? Well, it's a 70 reduction of wave height by a healthy willow forest. That's what we calculated with. We used this very simple modeling thing. On the y-axis is the incoming wave height, and then there is the distance. And at 0, the willow forest starts. And if you look at the gray upper line, that is the wave attenuation only over the surface without the willow forest. But then if you look at the green lines, those are the attenuated different incoming, or those are the different incoming wave heights that are attenuated in the willow forest. And you see what's interesting about it, if you look at point 0, is if we have waves coming in for 1 meter, a half a meter, or 20 centimeter, once you look at after 100 meters traveling through the forest, all these waves are attenuated till 10 centimeters. So it means that we can design for changing extra boundary conditions, changing hydraulic boundary conditions, and still design a levee for that 10 centimeters. So what happened in the end, it was a bit over-designed. There was 20 centimeters taken, and they made the overtopping safe levee. We had 2 species of willows there. So I don't know, to against pests and stuff. Basically this was this is now constructed in the Netherlands, and it functions and it works like this. And this polder was last autumn. It was full of water. Oh yeah, and then we implemented it already in reality, but we never did any tests with willows. So we figured that's what we really would like to do, test it with willows in our flume. In the meantime, the first marshes were in Hanover, but in the meantime, we got a new big flume in the Netherlands that is still the largest flume in the world now, but I think Hanover is now upgrading its flume, so they will probably be a bit larger again. It's the race of the flumes. It's a bit pathetic. I think there's longer flumes in the world, but we can make the highest artificial wave, and I think we can make a wave of 4.5 meters high. But that is not a nice wave for testing, actually, because that is a wave that's constantly breaking. So what we did is I was in contact with somebody who grows willows, because we still use willow branches for making these sort of pieces that we use actually in civil engineering construction for below water to stabilize the side of canals, for example. And he wanted to get rid of these 15-year-old willows, so they brought them to our to Deltares, and here they get towed off the truck. They actually had this machine to cut them out. So then we planted them in these boxes, and they sprouted again in spring. And then we placed them in our flume. So our big wave flume is like, it has, I think it's 130 meter long, and it's 5 meters wide and about 9.5 meters deep, I think. Oh, it's 7 meter wide, 9.5 meters deep. And it has a wave pedal on one side, and that pedal moves back and forth, and that generates a wave. And then in the back, we have a slope now, but that's a constructed slope, so we can move it if we want to. And what we did with the willows is we first had the wave coming in, then we made a platform with a really gradual slope. Then we had about 20 meter with no willows, so that the wave could sort of get used to the bottom. And then we had 40 meter of willow forest, 32 willows in there. And they were put like this in sand, and they were topped off with concrete. So we're not looking at uprooting of the willows, but we topped them over to make them stable. And again, we didn't dare to put maximum pressure on there. I will do that the next time. So this is what it looked like when they're underwater. We had 2 water levels. We had 3.5 meters and 4.5 meters on top of the platform with the willows on it. So we could also do slightly higher waves. And we tested with leaves, without leaves, with half of the branches. So we reduced the biomass, and a control without the willows. So we actually had to cut them all down in the end. And we de-leaf them manually. So because people want to know, nobody knew, is there any effect of the leaves? And nobody knew, and because we have the main storms in the winter, and then there's no leaves on the trees. I'm going to show you something of the experiments, but I'm not going to show you all the graphs with results, unfortunately. There we go. This is with 3.5 meters. So the wave travels through the canopy, and you see it already starts to sway slightly. And then we have, then after we de-leaf them, we started actually do higher waves. The maximum, or not the maximum wave height, we had, what it happens is if we put in a wave height of 1.5 meters, that's the average wave height. So it creates a spectrum with different wave heights around this 1.5 meters. So I think the maximum wave height we had in here was about 3 meters then in this spectrum. But the average wave height of these runs is 1.5 meter. I think the waves that you see here are a little bit higher. And they're the high end of the spectrum, look. And what happens here, look, with the branches. So it goes, now the water level is 4.5 meters, and the waves, you see some of them are breaking. So it means they're probably around over 2 meters or 2.5 meters, because they start feeding the bottom. And you see that the branches now start moving again 180 degrees. So we also find a big reduction in the attenuation of the waves where this happens. So I can show it again, and it's, and they're wooden branches basically. So it was not something that we really expected, because they look really rigid, but still they jump out again when the wave has passed by. So we see also a big reduction in the wave attenuation when this effect starts to occur. And basically what we find of these experiments are, and we still need to publish it, but we're an applied research institute and we don't have time for publishing, and we're not too good at it, I have to say. The wave reduction, what we found, is strongly dependent on the wave height and the wavelength. That's nothing new, because we knew that and we expected it. But it's also strongly dependent on the water level and in relation to the surface area it meets. So we see, for example, if we put the water level at 3 meters, then we see if the water level is 3 meters, then the wave runs through the most dense part of the canopy and we get most reduction. If we put that 4.5, the wave starts running through the top and we get a lot less reduction. And right now, what we found when we looked into our numerical models and we tried to validate this study is, in numerical model, the vegetation is represented as rigid cylinders. So, and these cylinders don't have side branches. So we actually found that we underestimate the whole biosurface area of a tree. We didn't find any effect of the leaves. That was basically could be neglected. When we removed the leaves, the attenuation was slightly lower. But it would be interesting to test it with another species that has larger leaves. These willows have tiny leaves that will just lie flat with the main wave direction. So the representation of surface area is key. We had a terrestrial laser scanner where we actually captured this whole forest. Next time, I think I want to redo it, of course, and I want to measure every tree from like every branch. We didn't do that yet because we were sort of hurried. This flume is planned. It's very, it's squeezed in. The planning is very crucial, squeezed in between two other experiments. We had too little time. Okay, what do we use the data for? Well, that is what we already did, because we can not sit on data too long and it needs to be flowed down into and help people actually. So what we want to do is validate the numerical models. That's what we already did, and propose new equations for how we include vegetation in these models. And what we also want to do, because we're a research institute, is embed the knowledge in design guidelines so that we can design better in the future, can design better combined vegetation levee systems. And then we want to use the knowledge to influence policies and to ensure that, so for example, one of these policies is the greenbelt policy that they have for mangroves, where they say that a greenbelt should be 100 meters wide, but with 100 meter, you have not reduced your wave of a wave of 2 meters significantly. So I think it should finally flow in there and result in that either the greenbelt policy changes to wider greenbelts, or that that there's no false promises about how much that mangrove forest then can reduce waves. But it would even be better if it leads to these combined designs, so that people with a mangrove forest also get some kind of small levee behind it. The future research, that is what we're doing now. So basically what we of course wanted to do when we started this is do this with mangroves, but we don't have mangroves in the Netherlands. So that is what I'm doing now. Now I do have mangroves in the Netherlands and we're growing them in a greenhouse. So it will take a couple of years still, I think 1 or 2 till they're big enough. You see they're already they're already small trees. We have a PhD student. She just made this little, that is actually working with all the results from these experiments. And basically focus on how can we easily capture biomass, how can we quickly measure it and then put it in a model, and how should we represent in a model. And what we're trying to do is to scale. So we don't want to keep doing these big flume experiments over and over again. We want to use it to scale, be able to scale it down better. So she used the terrestrial laser scan of vegetation models, and she rebuilt and 3D printed recently this little tree that is an exact match of one of the willow trees in the experiment. And then by changing less factors in scaling down, we can actually use a large scale to start having more experiments in small scale flumes, but only changing 1 or 2 parameters and not having a lot of unknowns. And there we want to use that to get better insight in the biomass drag and the drag coefficients, and how we should include these in numerical models. That is it.
Thanks. Thank you so much, Bregje. Really great to see engineering applied on this super large scale onto the question of ecosystem services. A lot of our students, we learn about it, we teach about it, and without quantifying just how much protection you get with that mangrove forest, I agree it's like a disservice to our knowledge, especially if we put someone in harm's way because we think it is safe. So we'll open it up to questions in both in the Zoom room as well as we got one from the YouTube. So I'll start with the question we got from YouTube, sort of technical. Scott Wassman asked, do the models that you're running use regular linear wave conditions?
Yeah. Well, I think, yeah, we use the models that we validate are, we have two models, Swan and XBeach, that we actually validated with these data, both the marshes and willows. And I think both models are based on linear wave theory, and vegetation is included by the Mendes and Losada vegetation equation.
All right, and a couple of questions coming into the chat. So Katie or Danielle, would you like to ask Dr. van Wesenbeeck yourself?
Okay, so Katie, if you want to start.
Sure. Thank you. First of all, thank you. That was really interesting. It's really, really cool to see what you're doing. With the willow tree flume experiment, you described that you put concrete down to prevent uprooting. How likely do you think uprooting would be an issue? If, like, obviously you can't say that, you didn't get to test that, but how likely do you think uprooting would be an issue if you were able to mimic like natural, normal root situations in dirt?
Yeah, yeah, good question. We put a lot of force sensors in one tree, so we could measure all the forces in the tree, and on the branches, on the stems. And then we now, one of the PhD is doing uprooting experiments by pulling on willows and also on mangroves. She already did a lot on mangroves, actually, pulling over mangrove trees. So we hope to translate forces on the tree to uproot experiments and get more insight in what you're answering. I think it is, for mangroves, it is relevant because when I work in mangrove areas, I always see toppled over trees, but there's a combination there with probably a reduction of sediment input so that they actually get sort of exposed there, I figure, because it always happens when there's like a sort of cliff. So when your profile in your before your mangrove, your mudflat profile moves from a convex profile to a concave profile, and it starts eroding and you get formation of a cliff, and mangroves start to be really exposed to wind, and then the side mangroves will start to topple over. For the Dutch floodplains, we do see, so willows topple over all the time. And then they basically, then they start sprouting from the side. They're really sort of resilient in that way. So they topple over, but then they stay alive and they actually make new branches from the side, and they can have multiple trees that start growing on the stem. So they do topple over, but it's but it doesn't mean they always become like floating biomass, right? Or that is what the engineers are extremely afraid of, that they get slammed on the dike or on the levee if we have grass levees in some areas.
Cool.
Thanks.
Thank you.
Great. Daniele, please go ahead.
Yeah, sure. Thanks a lot for the incredible talk. Basically, my question is, if you ever seen any kind of increase in the average water level due to setup in the first experiment you showed us. So the one with the levee and the marsh.
Yeah. It's a good question. I have to say it's very difficult to measure water level differences. But I have to recollect what we found the second one, because we had a lot of trouble in the second with the in both experiments. We could have seen it, and I think we had a lot of trouble with the measuring with the equipment and the accuracy of the equipment. So the accuracy doesn't allow to really measure, to really distinguish the setup. We looked in the last one, with the willows, we looked at run-up on the levee, and we measured it with 3 different methods, by eye, and with a camera, which is a new method. So there was a lot of difference in run-up, and the setup we weren't able to really look at that because of the inaccuracy in the measurements. And then you have to measure in front of your forest, right, and in the back. But there's good experiments by 2 of my colleagues and a former colleague, Ab van Dongeren and Arnold van Rooyen. And I think they measured in a flume, and they found with flexible vegetation and marsh kind vegetation, very big differences in setup. So I think the study is van Rooyen. You could check it there.
Bregje, it kind of
Thanks a lot.
reminds me of a question too. Most of the work was on wave and wave height, wave energy diminution, but just about, when we're thinking about tropical storms and hurricanes, I think a lot about surge, and I presume the physics is related, but also quite different. And so can you use your approach to think about surge reduction as well as wave reduction, or are they like parallel and you can estimate one from the surge reduction from what you've done so far?
Yeah, no, I don't think that is possible. I think a surge works really different. A surge is works like a really long wave, right? Like a tsunami wave. That is basically sort of a surge. And that's also, so for example, what happened during Hurricane Sandy, there was a bit of a surge there. So there was a wave effect and a surge effect. And there's a recent study out that looks at mangroves globally and surge. So how they reduce surge. So let's say there are numbers for it in models, but we don't use it. And I don't want to use it because with a surge, it depends a lot. If, for example, if you look at Sandy and what it did in New Jersey, it depends completely on how the surge enters your bay and how is the spatial configuration of your marsh. So for Katrina, there were model runs, and there it sort of shows that if you have like a creek in your marsh, the surge will just funnel through your creek. That is what the surge will do. So it's a different type of modeling, I think, you need for it, where the spatial configuration of your marsh becomes extremely important.
Great, thank you. Yeah.
But the basic results from the surge are that vegetation, so imagine if it would be a consistent marsh, it reduces your surge largely in the beginning, but it also, that's another effect, it depends a lot on the duration of your surge. So if your surge starts to be longer, well, it's just something you can already feel by physics, right? So then it starts to actually push up, there's increased roughness. It's low, then it will be reduced, but if it's longer, it actually will be enhanced.
Yeah,
So
I just wonder if they're, like the physiological characteristics of the vegetation or their roughness characteristics, like, are they sort of like equally good? Like more branches is good for surge, but more trunk is good for wave, and more leaves is good for, I mean, this is not based, it's just on a hypothesis, but that would be interesting. You have a model, yeah. You can play with that and test it. We have a question from Christine Angelini. She says, thanks for the talk, and asks if your team is doing any work to think about how the landscape scale configuration, a little bit like what you talked about with the tidal creek, but basically where to put these things in the best way to stack them or place them to reduce or to increase wave attenuation.
Yeah, nice question. There's a lot of ways to answer this one. I'm thinking how to answer it in a brief way. I think I was just talking with Andrew about the makeability of a landscape, right? It's only partly you can only partly engineer it or sort of influence it. And a marsh, for example, needs to have creeks. It needs to dewater, and there's this certain creek ratio that it has, right? Or same for a mangrove. We're looking at it more from a bit of a hydraulic and risk perspective. So we're mostly, and then what we do is we compare, okay, where could you basically reduce risk enough with vegetation only? Where would you need vegetation and a levee component to reduce it? And where would you actually say there's no vegetation present? The built environment reaches already to the end of the intertidal, right? Or so far into the sea that you would only do a levee. That's what we look at. We don't look at that exact configuration because I think there's so little known if you look from it physically. So what I want to do next is actually, so for example, we didn't look at biodiversity and how it would influence it, but I think that would be have a large effect, right? But we never model mangroves and an understory, for example. And I think that is one of the things I would really like to do, bring a biodiversity element in there. From a hydraulic perspective, but also from a, let's say, ecosystem functioning perspective. So that is the 100-meter greenbelt discussion. It may be enough for hydraulic purposes, but it will never be enough to be able to deal with natural dynamics, right? These systems erode and grow again in areas. It will never be enough to have the same species diversity as extensive mangrove. So I think these worlds still need to come together more.
Thanks, and I think we have time for one more question from Kathy. Do you want to ask Kathy?
Okay, I'm interested in the mangrove experiment. It seems to me that if you're planting mangroves in front of a levee, then you would be cutting off the freshwater flow that would help them to grow strong and tall enough to be effective. So would you test this by growing only scrubby mangroves, for instance, in the flume?
Yeah, good point. I think I'm not a big. I have to say I'm not a big fan of all the planting efforts that happen across the globe. So a lot happens on mudflats, right? And people forget that mudflat is also a habitat. So the aim is not to stimulate planting, but the first aim is, I think, to enable us to better calculate and conserve the mangroves that are there. Mm-hmm. So, and then I think your remark is a really right one. I think what I often see is that people actually in many countries, they construct the levee on the low water line while there's nobody living behind it. Behind this, there's the mangrove system. Mm-hmm. So if they want to construct a levee, at least it would be more logical to construct it behind the mangrove system on the line where the built environment is. And I think the question that indeed is then needed is where does the fresh water flow come from? In certain areas, it comes from rivers. And of course, those still need to be open then. In other areas where we find with mangroves, it's just the runoff from the land, right? Mm-hmm. So then I think if it's a land runoff, you could actually include that in a levee design in a way that you don't reduce it. But that is something that is not taken into account at all now in levee design. So it's it's a very good point.
Especially as we go to do restoration of, say, like shrimp aquaculture back to mangrove, and they basically have levees, small levees, and trying to build back in there, which can be very successful, but you do threaten hyper salinization. So. Bregje, thank you so much for your talk. Thanks everyone for coming today, and for everyone who watches it online. Excellent. Yes, give some little claps, real or virtual there. Great to meet you. So for everyone, next week we have Miles Medina, graduate from Ag and Bioengineering, and he's come up with a theory and some evidence that he can predict red tide blooms off the coast of Florida with organic nitrogen coming off the landscape. So maybe a good thing. If we can predict it, then we can prevent it or mitigate it. So come next week to check that out. And we will see you all then. Cheers, everyone.
Thank you.
Thank you.
Bye-bye.
I'll stop the recording.